Introduction to Parallel Coordinates Plot. Cartesian Coordinates Plot Construction. Before we describe parallel coordinates, let's refresh our memories in terms of how to construct a Cartesian coordinates plot. The table on the left shows 4 different points with the 2 variables x and y. Each point is located on the Cartesian coordinates on the right. Point 1, 0, 0 is located on the origin. To identify point 2, 2, 3, we move 2 units to the right of the origin and 3 units upwards from the origin. Point 3, minus 3 and 1 is located 3 units to the left of the origin and 1 unit above the origin. Also, we can follow a similar process for identifying point 4. What happens when you try to plot more than 2 variables on a Cartesian coordinates plot? When the point has more than 2 variables, you are not able to perceive and understand the point's variables on the Cartesian coordinate easily. The more variables you try to plot on the Cartesian coordinates, it quickly becomes infeasible. This is what the table looks like when we add 3 more variables called z, alpha and beta. The more dimensions we have, the more difficult it is to plot them on the Cartesian coordinates plot. Is there any alternative to the Cartesian coordinates that lets us plot multivariate data? We can use parallel coordinates plot as an alternative way to address the challenge of high dimensionality. Parallel coordinates plot construction. This is the same table we looked at earlier. Each line on the parallel coordinates plot represents one point in the table. This parallel coordinates plot shows 2 data attributes, x and y, with 2 parallel axes. The origins of the x and y axes are at 0. To find the x value of the point, we start at the origin and move n numbers of units along the x-axis and plot the first point on the x-axis. Similarly, we move n number of units along the y-axis from the origin and plot the second point on the y-axis. Then, we connect these points with an edge. For example, to draw the edge on the parallel coordinates represents point 2, we move 2 units up from the origin on the x-axis, and we move 3 units up from the origin on the y-axis. Then we connect the point on the x-axis to another point on the y-axis with an edge. Now we are going to introduce a software tool that we developed to demonstrate the correspondence between Cartesian coordinates and parallel coordinates plot. A tool to support parallel coordinates literacy. The tool links the points in Cartesian space with polylines in the parallel coordinate space. The tool aims to enable users to learn how to create and interpret parallel coordinates plots interactively, as well as facilitating the interpretation of multivariate data. A point appears on the Cartesian coordinates, and the corresponding edge appears on the parallel coordinates. If we want to define a point where the x and y values are equal to 2, we move 2 units to the right of the origin and 2 units upwards from the origin. Then we click on the mouse. Similarly, to identify a new point at -3 and -1, we move 3 units left of the origin and 1 unit below from the origin in the Cartesian coordinates and click on the mouse. When we identify a point in the Cartesian coordinates plot, the corresponding edge of the point appears on the parallel coordinates plot. This edge on the parallel coordinates represents the point. The edge starts from 2 units above from the origin on the x-axis and ends at 2 units above from the origin on the y-axis. To convey the link between the points and polylines, each point and polyline can be labeled with the same letter. The position of points and edges can be updated in both Cartesian and parallel coordinate plots. As I click and drag the points from right to left on the Cartesian coordinates, the x-coordinates decrease in both Cartesian and parallel coordinates plots. The same is true for the y position. When I drag the point from top to bottom on the Cartesian coordinates, y-coordinates decrease in both plots. Also, the x and y positions of the point can be altered by dragging the corresponding edge upwards or downwards along the x and y axes on the parallel coordinates. We can also draw edges between x and y position that creates points on the Cartesian coordinates with default size, color, and shape settings. Now we are going to demonstrate how to add more dimensions to both Cartesian and parallel coordinates plots. We start adding a third dimension called size, represent the size of each point. Adding a new dimension to the Cartesian coordinates adds a new axis to the parallel coordinates. A right-click menu can be used to display other variables of the points. We can show the size variable using a right-click menu and change the size of each point by dragging the mouse from right bottom corner of the point. So selecting the size variable from the right-click menu adds the size axis to the parallel coordinates. We can adjust the point size by dragging the mouse upwards or downwards on the size axis. A new dimension added to the Cartesian coordinates corresponds to a new parallel axis on the parallel coordinates. Therefore, it's so easy to represent multivariate data on the parallel coordinates. We can also add a fourth dimension. In this example, it will be the dimension of color which is mapped to the x position. Choosing the color option on the right-click menu adds the color axis on the parallel coordinates. The color of the point can be altered with another color on the color scale shown on the parallel coordinates plot. If we want, we can add a fifth variable. In this case, the fifth dimension is going to be the shape of the point. We can select 5 different shapes on the right-click menu, which adds the shape axis to the parallel coordinates. Here, how it looks like when we change the shape of the point, how that maps to the parallel coordinates. If we want to update the point shape, we can also drag the mouse from one shape to the another on the shape axis on the parallel coordinates. The axes relative to size, color, and shape can be toggled in and out for displaying the relationship between specific variables. I'm going to show you a parallel coordinates image with an example dataset. Let's look at the car dataset as a new example. The car dataset represents a collection of cars. In order to characterize the important attributes of each car, we record them in a spreadsheet. This car dataset shows 7 attributes such as cylinders, displacement, power, weight, acceleration, mileage values, and production year of different car models. Each polyline on the parallel coordinates represents an individual car model. Starting with top left of the image, we can read from left to right. For example, the first 3 car models have 8 cylinders. And then, if we follow the top edge, we can see the first car has 400 displacement value. If we continue tracing this edge, the power value is 160, the weight value is 4000, and acceleration value is 14. Identifying the data attribute relationship. The data attribute relationship can be defined as direct and indirect relationships or no relationship. This image also shows a similar car dataset with 5 attributes. If one data attribute value increases and the neighboring axis value decreases, this is how we find an indirect relationship in the parallel coordinates. When we look at the axis of mpg miles per gallon and cylinders, in general, mpg increases, the number of cylinders decreases. Therefore, we define this as an indirect relationship. Let's look at edges between horsepower and weight axes. In general, while horsepower increases, weight also increases. It results in many nearly horizontal edges. This is called a direct relationship. If the edges between axes don't provide any pattern, we can say that there is no relationship. In this example, we cannot identify any relationship between mpg and weight attributes. However, the order of axes can be changed to identify a new relationship.